very warm good morning to all of you. And first of all, am I audible?
Yes, you are very much audible.
So first of all, my thanks to Archana, Vijayalakshmi, and the entire executive committee for the invitation. And Archana for taking pains in hosting this event. And thank you so much. So as the title says, I will be speaking on representations of finite groups. It's going to be a very elementary level. The purpose is to introduce young students, master students, or beginners, PhD students to the subject, and if they are interested, they can study more and get into the subject. But the only thing I can do is in the 4 lectures. In the first lecture, I'll begin with some historical comments on the subject, how the subject got developed in the beginning. And now it is a very at a very advanced level, and a lot of research is being done in this area. And the idea is just to inculcate that feeling of the subject. So I'll just begin with what a representation is, and then I'll come to what made people think this way. And then in the next lecture, I will be doing some calculations and some basic theory of the subject. So representation is a branch of algebra that studies groups by representing their elements by matrices, invertible matrices, over some field. And the replacement is done in such a way. So I want to replace the elements of a group by elements of a concrete group. For example, matrices over F. And the replacement is done in such a way that the binary operation in G is replaced by the multiplication of the matrices. So what's the representation this way? So the idea is to replace an abstract group. I'm talking of finite groups only in this entire course, okay, in all the 4 lectures. The idea is to replace group elements by matrices so that the binary operation in G is replaced by multiplication of GLNF, matrices in GLNF. GLNF is n cross n, invertible matrices over a field F, which is a group. And so what I'm saying is that a representation is a homomorphism from G to GLNF. It's a homomorphism from G to GLNF, this. Because the multiplication in G, I want to replace it with the multiplication in GNF. So it's a homomorphism from G to GLNF. So N is called the degree of this, N is called the degree of this representation. The idea is to use the knowledge of this GLNF to get information about the group G. So what is the character? Given this representation of G, given this homomorphism from G to GLNF, given this homomorphism from G to GLNF, then you look at, for each G, there is an invertible n cross n matrix over F. You take the trace of that matrix. So I'm saying G goes to TG. And so you take the trace of that matrix, and this is called the character of T. So G going to TG is your homomorphism. And so this is G going to TG. This is your homomorphism. So if you take the trace of this matrix, then this is what the character is. I will do this in the next lecture in more details, but this is the definition of a representation and a character. So who are the principal contributors in the early stages? The Frobenius. It is the theory initiated by Frobenius and Burnside, and then many other people joined, and this development was done in the late 19th century. So what made Frobenius and Burnside to develop this subject? I will just tell you that story. So this is Frobenius, late 19th century, and this is Burnside. The others with whom their work was intertwined was Artin, Carton, Dedekind. Dedekind was the one who raised the question. Mashike, Moulin, Nakayama, Noether. So all these works were put together and the theory got developed. And the importance of the subject is due to its large variety of applications, not only in mathematics, but to various branches: physics, chemistry, cryptography, coding, computer science, robotics, medicine science. So you will see that if you search for the applications of representation theory in medicine science, if you just do the Google search, you will be surprised to see the amount of papers in that area. So, and robotic science also, to see the movements of the robot, this theory is used. So every subject has two important aspects. One is its history, why the subject got developed, and how the creators use the tools available at that time. And what is of course, the modern version of the subject, how this is at the present time, how the things have got refined over the time. And so a proper coverage of the history of representation theory, in my opinion, requires a full book, starting with the pioneering work of Moulin, Carton, Dedekind, Frobenius, Burnside, Schur, Noether, Brouwer. So these are all the people who were in the early stages, but Frobenius and Burnside were the Dedekind. Frobenius and Burnside were the on the top in the history of representation theory. So what I can give you is that a quick snapshot of a big story focusing on the origin of representation theory. So the subject was, as I told you, the subject was born during the late 19th century when Frobenius wrote a letter to Dedekind on April 12, 1896. So what was contained in that letter? Why Frobenius wrote this letter to Dedekind? I will just tell you that story. What was behind that? So actually, some people call this April 12th, 1896 as the birth date of representation theory. Usually a subject does not have any particular date assigned to it, but representation theory, the historian says that it was this date that when Frobenius sent this message to Dedekind. So this was Dedekind. Dedekind was before Frobenius, in the few years senior to Frobenius. During he was at the peak of his career at that time, during 19th century, middle and end of 19th century. So the subject group theory was half a century old during the late 19th century, because it is the early 19th century mostly got developed at that time. So it was about half a century old, and if we regard group theory as originating from the time of Gauss, Cauchy, Klein, Galois, and so on. So these were the people at that time. Dedekind, you must have learned in your courses. His name is associated with number theory. He was a leader in abstract algebra. He was a leader in ring theory, particularly ideal theory. That was all his development. Real numbers through Dedekind cut, that is through him. And then modern set theory, axiomatic foundation of arithmetic. All this is dedicated to Dedekind. He was the creator of those things. And Gauss, you have learned a lot about Gauss. Gauss was prior to Dedekind. 1777 to 1855. He survived till 1855. And Gauss was the greatest mathematician of his time. And you know that he showed that a regular polygon can be constructed with regular and compass if the number of sides is product of distinct Fermat's prime and a power of 2. So this was a problem of ancient Greeks, and he solved that problem. And so that was the time. And then Cauchy was a French mathematician, very famous for waves, mechanics, Taylor's theorem, Cauchy integral formula, Cauchy's results in group theory. And then Galois was also at that same time, and he was a politically activist and died due to political turmoil. But still in his teens, he developed necessary and sufficient conditions for the solvability of polynomials by radicals, which was a problem of open problem for more than 350 years, and on the solvability of polynomials. So all this was happening. And in 1870, so I'll just tell you what was happening in the late 19th century. In 1870, Jordan and Calais' first treatise on group theory appeared. Both the books were on permutation groups. So this is the first time that such a thing appeared in the literature. 1872, Kleins used group theory for studying various geometries. And in 1872, Silo published the first proofs of his famous theorems. Abstract groups were treated later, perhaps for the first time in the textbook by Weber. Although Kelly defined abstract group, but that was lost, and it was for the first time appeared in the Weber's book that people, it got attracted. And during this period, group theory was so immature that Kelly, well-known group theorist, confused his readers by listing 3 groups of order 6 in his paper of 1878. So group theory was just being developed at that time. So even that clarity was not there. And as far as the representations is concerned, there was not much in evidence before 1870. In 1870s and 80s, clients certainly used matrices to realize groups, but there was no hint at a possible theory that it can be developed. And during this time, there was a tradition of assigning numerical values to algebraic structures. So I will just come to that. In number theory, various things were happening that if you have an algebraic structure, you assign a numerical value to the structure so that lot of invariants of that algebraic structure are contained in that numerical value. So for example, look at Legendre symbol in 1978. Legendre defined this symbol AP, you have done in your group theory or your number theory courses, that the symbol takes the value 1 if x square congruent to A mod P has a solution, and -1 when there is no solution. And so it's the first instance of a character on ZP, Z mod PZ. But so Gauss also used, so there was a numerical value assigned to the solvability of quadratic equations modulo P. And Gauss used similar symbols in dealing with Gauss sums and with binary quadratic forms, but the character values were usually the roots of unity. So initially, it was not that representations were defined first and then characters were defined. First, characters were constructed and then representations were defined later. So in Dirichlet's work on primes in an arithmetic progression, Dirichlet L series also figures characters in its values. So there was some tradition of assigning numerical values to algebraic structures, and then the things were being studied. So in number theory, there was a notion of discriminant of a number field, and that was given by Dedekind himself. So let's try to see what inspired Dedekind. And that was his question which he raised to Frobenius, and as an answer to which theory got developed. This was Dedekind knew the circulant matrices, that you look at a matrix of the form. You have, this is the first row, x0, x1, x2, xn minus 1. These are just variables. Xi's are just variables. And now you cyclically rotate them, xn minus 1, x0, and then in the next row again give one more cyclic rotation, and so on. So this is called circulant matrix, and its determinant is called circulant of order n. Xi's are indeterminate. And circulants of order 2. So you have to take determinant of this 2 cross 2 matrix, and it factors into 2 linear factors, x0 minus x1 and x0 plus x1. And that was the beginning. Now look at circulants of order 3. So x0, x1, x2, and then cyclically permute the rows. And this also factors into 3 linear factors. And then circulants of order n. So it was proved by Cremona, 1856, that a circulant of order n is a product of n linear factors. And so these were the character values basically. So the work of Dedekind was led to an extension of the circulant by consideration in algebraic number theory. So instead of cyclically rotating them, you give a group action. The discriminant of set of n numbers, alpha 1, alpha 2, alpha n of k is defined as the square of the determinant of this, where sigma i's are taken from the Galois group, and this was a motivation for the group determinant. So what Dedekind had reasons to think was that, so suppose your alpha i's, these alpha 1, alpha 2, alpha n, so he had an extension k of f, and then alpha i's was a basis of k over f. And now you take a normal element of the extension, and then you apply sigma i's and take the determinant of this. And so this is how discriminant of a number field was defined by Dedekind. So now he said that you forget about this alpha. You forget about this alpha and look at the matrix. If you have a group G, so you forget about this alpha, and if you have a group G, you look at the matrix whose first entry is x1, second entry is x12. X12 is the multiplication of the first and the second element of the group, and then x1n, then x21. X21 is the multiplication of 21 is the multiplication of the second and the second element of the group, and you form a matrix like this and take its determinant. And that was, so this is Dedekind's notion of a group matrix, that you take any finite group G and you take variables xg, and form the matrix xgh inverse, and take the determinant of this, and he called that as a group determinant and denoted it by theta g, and it's a homogeneous polynomial in xg's. So Dedekind proved that if G is an abelian group, then this theta g factors into linear factors, similar to the factorization of the circulant matrices, that if G is an abelian group, then this factors into linear factors. And what he was guessing was, he computed also for the non-abelian group S3 and Q8, and what he observed was that the factorization of group determinant is not into linear factors, is not always into linear factors, and he believed that there is a connection between the normal subgroups of the group and the linear factors of the group determinant. So that was, he was thinking that there is some kind of connection between normal subgroups and this. He could not prove that, but then he had two examples to illustrate to Frobenius that, see, this is happening and this is his guess. And so on March 25th, 1896, Dedekind wrote a letter to Frobenius about factorization of theta g, what he has done for abelian groups, what he has for S3 and quaternions, and the problems he faced, and he invited Frobenius to look into the matter. On March 25th, he wrote a letter, and within a month, Frobenius acted on it, and the theory was developed. Frobenius was at the peak of his career and had achieved great fame at that time. Frobenius made a name for himself by contributing to a wide variety of topics: linear differential equations, elliptic and theta functions. He was quite good with determinants and matrix theory by linear forms. That is why Dedekind posed this question to Frobenius. In 1887, Frobenius published first proof of Silo's theorem for abstract groups. Silo published his proof for the theorems when your groups are symmetric groups. And it was Frobenius who published the first proofs of Silo's theorem for abstract groups. Frobenius' inductive proof for the existence of Silo subgroups using class equation is still used today. His notion of double cosets, Cauchy-Frobenius counting formula in combinatorics was very popular. Frobenius was very quick in coming to grips with the problem posed by Dedekind. So, in less than a month, Frobenius invented general character theory of finite groups to solve the factorization problem of this theta g. He had a very good answer, which he gave. He reported his findings to Dedekind on April 12th, 17th, 26th of 1896. Just after a month, he did all that. It was so quick. And so these letters are kept in the archives of the Technical University as the first records of Dedekind Frobenius correspondence. There was a lot of correspondence those days between Dedekind and Frobenius, but these are the three important letters where he informed the entire theory to Dedekind. So Frobenius' first definition of non-abelian character was given via the eigenvalues of a certain set of commuting matrices. So first characters were defined, not the representations. So they were defined like the eigenvalues of certain commuting matrices. And this work led Frobenius to formulate in 1897 the modern definition of matrix representation and character. So this work of Frobenius blossomed into amazingly rich subject. Later, of course, many people joined. Burnside came, and Emmy Noether came, Schur came, Brouwer came, and they all contributed very immensely to this area. And then lots of applications were seen. So this work of Frobenius blossomed into a very rich subject, representation theory of finite groups. It's a 125-year-old subject only. And so now this was correspondence between Dedekind and Frobenius. So now I am going to, I told you two main joints, Frobenius and Burnside. So now I will tell you the story of Burnside. So what he did at that time. And so Burnside was born in London. This Frobenius was a German mathematician, and this was an Englishman, Burnside. He was born in London, received traditional university education in St. John's and Pembroke College in Cambridge, worked at Cambridge and Greenwich, served long time in London Mathematical Society. Burnside's early training was in applied mathematics, which at that time was meant essentially the applications of analysis. So that time applied was just the applications of analysis, function theory, differential equations to theoretical physics, such as kinematics, elasticity, theory of gases, etc. So for the first 15 years, Burnside published papers in applied areas, elliptic and automorphic functions, differential geometry. He was elected fellow of the Royal Society of London. During late 19th century, that was the time when Frobenius worked on character theory or on the question posed by Dedekind. Burnside's before that, of course, before those letters, several years before those letters, because that time Burnside's book came. So during the late 19th century, Burnside interest shifted to group theory, and he published his group theory book in 1897. So that year, when Frobenius was developing the character theory of finite groups, that year, this Burnside's book on group theory came. In his book, Burnside proved the following. Groups of order P to the A, Q to the B, A less than or equal to 2 are solvable. Okay. So groups of order P into Q to the B are solvable, P square into Q to the B are solvable, Q to the B are solvable, but not beyond that he could not prove at that time. And then groups whose Sylow subgroups are abelian are solvable. Solvable groups occur in the context of Galois' work, solvability of polynomials by radicals. So solvable groups were important in the context of solvability of polynomials by radicals. So non-abelian simple groups, and that was also the attraction. Non-abelian simple groups have even order if order of G is a product of less than 6 primes. Burnside could prove that. You know Field-Thompson's theorem now, but I'll just come to that. But Burnside could prove at that time that if the order of G is less than 6 primes, then non-abelian groups of even order do not occur. So Burnside's book closing remark says that there is no known simple group whose order contains fewer than 3 primes, and investigation into this direction is also likely to lead to results of interest and importance. So basically, Burnside raised 2 important questions: that there is no simple group whose order is fewer than 3 primes, and simple groups of odd order do not exist. That was his remark, and he checked it for the groups of order less than 4,000. So this was of interest to him. And after reading Frobenius' papers on characters, Frobenius published his work at that time immediately. Burnside saw immediate relevance of Frobenius' new theory to finite simple groups. That is why Burnside got interested into the Frobenius work. By analyzing the structure of complex group algebra, Burnside rediscovered all the main results of Frobenius using the idea of a regular representation. I will define regular representation in my next talk. So Burnside did not claim the results to be new, although he proved them entirely in his own style, in his own way. He did not prove them to be new. In one of his papers, he wrote, "The present paper has been written with the intention of introducing this new development to the readers. It is not original, as the results arrived at are, with 1 or 2 slight exceptions due to Herr Frobenius, Professor Frobenius, And the modes of proof, however, are in general quite distinct from those of Frobenius. So he did not claim the new results, although his technique was entirely new, and that is how it is done today, the way Burnside did it. And Burnside gave a detailed investigation into the nature of irreducible representations and their applications. So he defined irreducible, basically coming from the irreducible factors of the group determinant. So-called irreducible characters, irreducible representations, those kind of things were defined, which I will define with you. But I will define in the way it is taught today in the modern language. And so Burnside arrived at some famous results. Important results, got famous, of course, later. Groups of order P to the A, Q to the B are solvable. He could prove that with the character theory. So earlier he had was PQ square, P and a power of Q, P square into a power of Q. And then now he could prove in general using character theory that groups of order P to the A, Q to the B are solvable. And then he also proved that the number of real valued irreducible characters of G is equal to the real conjugacy classes of G. So all those things were defined. So basically he showed the importance of Frobenius' development of character theory immediately by applying the theory to finite groups. So that is why people realize the importance of the subject. If order of G is even, he proved that there exists a non-trivial real valued irreducible character. And then if chi is a faithful character of G, then any irreducible character of G is a constituent of chi. That was an important result. If G has conjugacy class size P to the R, then G is not simple, because this Burnside was in a search of simple groups. So he was developing the criteria which make the group simple. And so Burnside himself proved the first problem which he posed, that the groups of order P to the A, Q to the B are solvable. And this is the important result which is done in the first course on representation theory, wherever it is taught in any university or colleges, usually at a master's or at a pre-PhD level. Master's level, that groups of order P to the A, Q to the B are solvable. Solvability of groups of odd order. That was also the question which Burnside posed in his book of 1897. That proved to be very, very difficult. But Burnside again wrote in one of his papers that character theory is going to be helpful in proving this. And this is what he guesses, that a groups of odd order must be solvable. This was answered by Fiat and Thompson in 1963 in their 60 pages paper using character theory. And Fiat and Thompson received Cole Prize for their work in 1965. And later, in 1970, Thompson received Fields Medal for subsequent work on finite simple groups, and entire done with character theory initiated by Frobenius Burnside. And all of this work culminated later into the classification of finite simple groups in 1980s. So the beautiful subject got developed. And in 1994, Zelmanev received Fields Medal on another problem posed by Burnside. So this tremendous legacy, the work in representation theory initiated by Frobenius and Burnside, so spawned the work of field medalists. So what a tremendous legacy to mathematics they have given. When Dedekind wrote a letter to Frobenius worked on it, and then Burnside applied the subject to finite groups. And then people realized the importance of the subject. And today these theories provide basic tools for various branches of mathematics and extremely used in many branches of applied fields, not only in mathematics, in various branches. So if you just do Google search, you will get several papers on the applications of representation theory. And this amazingly diverse applications made possible by purely theoretical work provides a striking instance of the effectiveness of mathematics. So how effective is the mathematics that initially one just thinks of a problem, develops the theory without having any applications in mind, but then over the years, after 100 years, so many applications are seen, and there is so much development in the subject. And so these are the books for the reference. If you want to read Pioneers of Representation Theory by Curtis. It's a beautiful book written by Curtis on Burnside, Frobenius, Burnside, Schuer and Brouwer. Schuer and Brouwer work is also very important. Brouwer worked on the modular representation theory. And these are also important papers in the notices of American Mathematical Society. If you want to read Representations of Finite Groups, 100 Years, Part 1. This is by T.Y. Lamb. You just do Google search, it's freely available, so you will get the PDF. Otherwise, it's in the notices of AMS, American Math Society. And then the same paper by Lamb, Part 2. Actually, this one, Part 1 is on Frobenius, and Part 2 is on Burnside. And this Conard origin of representation theory, this is a preprint. This is a preprint available online if you just do Google search. And he beautifully explains the Dedekind way of thinking on circulant matrices, discriminant of a number field, and a very nice survey of the subject, origins of the subject. You will like reading these articles, and you will get more information on this, because I just gave you a snapshot just to create the interest. But if you want to read more, you will get interested into the history, and hope you are motivated to learn the subject. And so I will, from now after this, I will be just teaching you the way the subject is taught today, and just the important highlights of the subject, important notions of the subject. How far I can reach in these 4 lectures, we will see.